Episode 1. The Learning Loop. Imagine dropping a robot into a maze it's never seen before. No map, no instructions, no teacher standing over its shoulder saying, "Go left." The only feedback it gets is a signal. Positive when it does something good, negative when it doesn't. And somehow, through nothing but trial and error, it learns to navigate perfectly. That's reinforcement learning. And by the end of this episode, you'll understand the fundamental loop that makes it all work. Welcome to the essence of reinforcement learning. This is the first episode of a course that will take you from knowing nothing about RL to deeply understanding the algorithms that taught machines to play Atari, beat world champions at Go, and even help train the large language models you use every day. We're starting at the very beginning. No prerequisites beyond basic intuition. If you've ever trained a dog with treats, you already understand the core idea. In machine learning, there are three major paradigms. Supervised learning uses labeled examples. Unsupervised learning finds patterns in data. And reinforcement learning is different. It learns from interaction with an environment, guided by a reward signal. Here's the fundamental picture. Every reinforcement learning problem has two players. The agent is the learner. It's the thing making decisions. Could be a robot, a game player, a trading algorithm, or a recommendation system. The environment is everything else. It's the world the agent lives in. The maze, the game board, the stock market, and they interact in a loop. At each step, the agent observes the current state of the environment. Based on that state, it chooses an action. The environment responds by transitioning to a new state and providing a reward signal. Then the loop repeats. State, action, reward. Next state, action, reward. This is the heartbeat of reinforcement learning. Everything we build in this course will be about optimizing behavior within this loop. A state captures everything the agent needs to know about the current situation. In a grid world, it might be the agent's position, row 2, column 3. But states can be much more complex. Think about chess. The state isn't just where your pieces are. It's the position of every piece on the board, both yours and your opponent's. Every pawn, every bishop, every rook. That means the number of possible chess states is astronomical, more than the number of atoms in the observable universe. And that robot? Its state includes joint angles, velocities, sensor readings from cameras, and touch sensors. Dozens of numbers, all changing continuously. But here's the beautiful thing about our grid world. The state is just two numbers, a row and a column. Same framework, vastly different complexity. The set of all possible states is called the state space. We write it with a capital S. And for our grid world, it contains exactly 25 states. An action is what the agent can do. In our grid world, the agent can move up, down, left, or right. When the agent considers its options, it looks at the current state and asks, what moves are available? 4 choices: up, down, left, right. Each action changes the state in a predictable way, usually. And what happens if the agent tries to walk through a wall? Nice try, but the environment doesn't allow it. The agent stays put. It still uses its turn, still gets a step penalty, but the environment decides the consequences. Now, our grid world has what we call a discrete action space. 4 distinct choices. But in robotics, actions are often continuous. A motor might apply any torque between 0 and 100. The action isn't a choice from a menu. It's a number that can be any value in a range. Same framework, whether you have 4 discrete choices or infinite continuous ones. The agent picks an action, and the environment responds. The set of all possible actions is the action space, written as capital A. For our grid world, that's just 4 moves, but you already know it can be much bigger. And sometimes, the action space depends on the state. If you're next to a wall, one of your 4 moves has no effect. The environment enforces the rules, not the agent. So our agent can see where it is, and it can choose where to go. But how does it know what's good and what's bad? The reward is a single number that tells the agent how good or bad the last transition was. Reach the goal, +10. Fall into a trap, -5. Every other step, -1. A small penalty that encourages the agent to find the goal quickly rather than wandering forever. Here's the critical insight. The reward signal is the only feedback the agent gets. Nobody tells it which action was correct. Nobody shows it the optimal path. The agent has to figure out, from rewards alone, which actions lead to good outcomes. This is what makes RL fundamentally different from supervised learning. There's no teacher. There's no data set of correct answers. There's only experience and consequences. Let's watch it happen. Here's a simple 5x5 grid world. The agent starts in the top left corner. The goal is in the bottom right. There are walls the agent can't pass through, and a trap that gives a penalty. First, let's see what happens when the agent picks actions completely at random. It stumbles around, hits walls, sometimes falls into the trap. Eventually, by pure chance, it might reach the goal. But it has no memory and no strategy. It doesn't learn anything. Let's slow way down and trace exactly what happens in a single step. The agent is at position row 1, column 0. It looks at its options, up, down, left, right. Based on its current estimates, it picks down. The agent moves to row 2, column 0. The environment gives a reward of -1. A step penalty. It's not at the goal yet. Now the learning happens. The agent has a tuple, a state, an action, a reward, and a next state. It nudges its estimate for moving down from row 1, column 0 slightly, from 0 to -0.1. That's it. One step, one tiny update. But multiply this across thousands of steps, across hundreds of episodes, and something remarkable happens. Patterns emerge, paths crystallize. The agent builds a complete map of which actions are good in which states, without anyone ever telling it the answer. That was one step, but what does it look like when we let the agent run for 200 full episodes? Now, let's give it the ability to learn. After each experience, after each state, action, reward, and next state, the agent updates its internal estimates of how good each action is in each state. Watch what happens over 200 episodes. In the beginning, everything is uncertain, but gradually, the values near the goal get brighter, the values near the trap get darker, and arrows appear pointing towards the goal. After enough experience, the agent has learned a policy, a complete strategy that maps every state to an action. And look, it now takes the shortest safe path to the goal, automatically avoiding the trap and the walls. Nobody programmed this path. It emerged from the learning loop. After 200 episodes, the agent has learned a clear policy. It knows the best action in every state. But there's a problem, a tension that sits at the very heart of reinforcement learning. What if there's a better path the agent has never tried? And this brings us to the first big tension In reinforcement learning, the exploration-exploitation dilemma. If the agent always picks the action it currently thinks is best, it exploits its knowledge, but it might miss even better options it's never tried. If the agent always picks randomly, it explores, but it never uses what it's learned. The solution? Do both. A common approach is called epsilon greedy. With probability epsilon, say 10%, pick a random action. The rest of the time, go with the best known action. This way, the agent mostly follows its learned policy, but occasionally tries something new. And as it learns more, it can reduce epsilon, exploring less and exploiting more. This tension between exploring and exploiting isn't just an RL problem. It shows up everywhere. Trying new restaurants versus going to your favorite, testing new strategies versus sticking with what works. RL gives us a mathematical framework for thinking about it. Let's lock in the key ideas from this episode. First, reinforcement learning is about learning from interaction. An agent acts in an environment and learns from the reward signal. Second, the agent-environment loop is the foundation. State, action, reward, next state. Everything builds on this. Third, exploration and exploitation must be balanced. The agent needs to try new things while also using what it's learned. In the next episode, we'll formalize this loop into something called a Markov decision process, the mathematical framework that makes everything precise. We'll define transition probabilities, the discount factor, and what it really means for a policy to be optimal. See you there.